Welcome, this is Mr. Anderson, and today we're talking about operations with radicals. So, operations, what am I talking about? Well, I'm talking about adding and subtracting and multiplying them and dividing them. And then radicals. Okay, so we got these radicals, and let's talk about the terminology a little bit. So this right here, we got our radical sign. And this number that's right over here in the notch of that radical sign, that's called the index. And underneath that radical sign is what we call the radicand. We have our index, the radical sign, and then radical sign, and then the radicand. Okay, so let's talk about some rules that we need to know. Okay, now one of the first things I guess that we learn is that is this right here that the nth root of x to the n equals x. All right, the identity rule of radicals. Now, wait a second. Okay, so like for example, right, the square root of x squared equals x. Right? Because x squared is a perfect square. You think of it like a perfect square or a pair, right? Or I could say the cubed root of x cubed is equal to x, right? If the index and that exponent on the radicand, if they match up, right, those are going to like cancel each other out. And that's what that rule is saying, the identity rule. Okay, another thing that we know is that if we are adding or subtracting radicals, so let's say we have, let's call this the eighth root of x plus, well, let's say 2 times root a of x plus 3 times root a of x is going to equal 5 root a of x. Right? We have to have, if we're going to add radicals, right, the index and the radicand have to match up. They have to match up. Example, we had like a 2 of the square roots of 3 plus 4 of the square roots of 3 is going to equal 6, 6 of the square roots of 3. Right? We couldn't have 2 of the square roots of 3 plus 5 of the square roots of 2. We can't combine those, right? Yes, the indexes are the same, right? They're both root 2, the square root. All right, but the radicands are not the same here. The 3 and the 2. We can't combine those. That's already as simple as we can get it. Okay, now we also want to take a look at this product and quotient rule. Okay, so product rule. If I have, and we've done a little bit of this already, but let's say that I have the square root, or let's put the nth root of x times the nth root of y. Right? I can, since they're both the same root, I can combine that underneath one radical, one nth root. Call that x times y, the nth root of x times y. So example here, let's say that we had the third root of 5 times the third root of x, and we could call that the third root of 5x. right? And this goes the other way around too. If I had, say, the square root of 16x, right? I can split that apart. I can say that is the square root of 16 times the square root of x. Well, the square root of 16 I know is 4, and I can't simplify that square root of x at all. That remains the square root of x. So notice I broke this apart into multiplying two of the same index radicals. All right, and here I had two of the same index radicals, and I combined them together underneath one of the same index radicals. They're both cube roots, so I combined them underneath one cube root. Bottom here, square root of 16x. I split it apart into two different square roots over there. Okay, so the quotient rule, very similar. All right, let's say that we have the nth root of x over the nth root of y. We can call that the nth root of x over y. All right, they're both the same index, and so I can combine that into one radical with x over y, or x divided by y. And that goes the other way around as well. All right, so let's look at it both ways. Let's say that we have, let's say we've got the square root of 32x cubed over the square root of 2x. Okay, they are both square roots, so I can combine that underneath one of these. So 32x cubed over 2x. Now notice the simplification that I can do on that radicand. 32 divided by 2 is 16. X cubed divided by x, one of those x's is going to cancel out, so that's x squared. And now look what I have. I've got the square root of 16x squared, or, hey, let's use our product rule and split that apart. We call that the square root of 16 times the square root of x squared. All right, the square root of 16 is 4. The square root of x squared is x. I have 4x. All right, that quotient rule helped us out there. Let's take that the other way around here. And let's go from a fraction underneath the radical, where the radicand is, and let's split it apart into two. So what would that look like? Let's say that we have the square root of, let's just use numbers this time. And let's say I came up to you, I asked you, hey, what is the square root of 25 ninths? 25 ninths? I don't know what the square root of 25 ninths is. But hey, you can use your quotient rule and split that apart. You can say, hey, that is the square root of 25 over the square root of 9. And I do know what the square root of 25 is. That's 5. And I do know what the square root of 9 is. That's 3. Right? The square root of 25 ninths is 5 thirds. Okay, so looking at these different rules here, let's see some examples of what we might do. Here's our first example. Let's say we need to simplify this radicals here. These radicals. We've got multiplication. That's the operation that we are performing here. This says 3 times square root of 5y times 8 times square root of 10yz. All right, well, I can multiply the 3 and the 8. That's 24. And I can also combine, they're both square roots, right? So using my product rule, I can combine all that stuff underneath one radical, right? 5 times y times 10 times y times z. I have all that combined underneath one radical. Let's see. So I have 24 and I have 5 times y. This is 10. Let's break this down to 5 times 2. Then I have another y and a number z. Now, when I'm simplifying radicals, I'm looking for pairs or perfect squares. And here, I've really broken it down into the smallest factorization I can. But I see that I have a pair of 5s here. I got a pair of 5s. I can take that outside the radical, or I could use my product rule and separate it out. 24 times the square root of 5 times 5. All right, and then I've got a pair of y's there, all right? I can take that outside the radical as well. And I will separate that out. Y times y. And then I got a square root of 2 and a square root of z. Z looks really close to my 2. Okay. Square root of 5 times 5. We know that that is 5. And the square root of y times y, we know that that is y. Can't simplify that square root of 2 any, and can't simplify that square root of z any. I'll put those both underneath the same square root. So 24 times 5. What do we got there? 5 times 20, that's 100 plus 20, so that's 120y square root to z. That is our simplification. Okay, let's take a look at another example. Well, this is an interesting one. We've got the square root of 2536 times r squared times t. Okay, well, let's break this apart a little bit. I know by the product rule, I can separate out that fraction there, 2536, as I multiplied it times r squared, and then I multiplied that times t. Okay, now look at this square root of 25 over 36. Now I'm going to use my quotient rule for that one, and I'll call that the square root of 25 over the square root of 36. Right? I also know that the square root of r squared, right, the index of 2, the understood 2 right here, matches up with that exponent of the radicand of 2. Those cancel each other out. Right, r squared being a perfect square, I know that the square root of r squared is r. And I can't simplify that square root of t anymore. Just leave that square root of t. All right, so we've got square root of 25. Hey, I know what that is. That is 5. And the square root of 36, that is 6. So I got 5/6 r times your square root of t. That's my final answer. Let's take a look at this example. Man, this looks complicated. We got 7 square roots of 2 minus 3 square roots of 3. We've got that difference times 4 square roots of 6 plus 3 square roots of 12. All right, those two groups multiplied together. You may recognize this. We're going to have to do FOIL, right, or double distribution. Remember, like something like this. We got x minus 2 times x plus 5, right? And then you have to distribute the x with the x and the 5, and then you got to distribute the negative 2 with the x and the 5, and you add all those terms together. Okay, we're going to have to do the same thing with this over here. I'm going to have to distribute in this first grouping, right? I've got 2 different terms here. I've got 7 square roots of 2 minus 3 square roots of 3. I'm going to have to distribute that 7 square roots of 2 with the 4 square roots of 6, and then the 3 square roots of 12. And then I got to do the same thing with that negative 3 square roots of 3. I got to distribute that negative 3 square roots of 3 with the 4 square roots of 6, and that's 3 square roots of 12. All right, so what is that going to look like here? So I have, let's just write it all out. Let's not simplify anything. I got 7 square roots of 2 times 4 square roots of 6. Okay, and then I got 7 square roots of 2 times 3 square roots of 12. And then I have negative 3 square roots of 3 times a positive 4 square roots of 6. And then I have a negative 3 square roots of 3 times a 3 square roots of 12. Okay. Let's multiply each one of these terms. So I got 7 square roots of 2 times 4 square roots of 6. I can multiply the 7 and the 4 to give me 28. And they're both square roots, so I can put the square root of 2 and square root of 6. I can multiply those together underneath one square root. So that's 28 square roots of 12. The next term here I have 7 square roots of 2 times 3 square roots of 12. That's 7 times the 3 is 21. And then underneath the square root, I have square root of 2 times square root of 12 to give me square root of 24. Next term, minus 3 square roots of 3 times 4 square roots of 6. So 3 times 4 is 12. And then underneath the radical, 3 times 6 is 18. And the last term, 3 square roots of 3, 3 square roots of 12. I got 3 times 3 is 9. And then 3 times 12 underneath the radical is 36. All right, let's see what we can simplify. Right now, I see I got square root of 12, square root of 24, square root of 18, and square root of 36. They're all square roots, but none of the radicands match. So as it is right now, I can't add anything, but we may be able to combine some of these if I can reduce some of these radicals down to be the same radicand. So let's see, 28 square roots of 12. I can break that square root of 12 down into square root of 4 times square root of 3. Let's see, 21 square roots of 24. What's a perfect square root that goes in there? Well, that's 4. 4 times 6 would give me 24. Well, I could take that perfect square of 4 out. Let's see, then we have minus 12 square roots of 18. So that'd be 12. And underneath the radicand, 9 times 2 is 18. 9 is a perfect square. So I'll write that square root of 9 times 2. And the last one we have 9. And square root of 36 by that is a perfect square. I'll just write that as 6. Square root of 36 is 6. So let's go back through here. I got 28. And then underneath the radical, I have 4 times 3. Square root of 4 is 2. And then I have to, that square root of 3 is going to remain the same. Then I've got 21 times square root of 4 times 6. So square root of 4 is 2. And then I can't do anything with that square root of 6. That stays underneath the radical. Minus 12 times square root of 9 times 2. Square root of 9 is 3. And can't do anything with that square root of 2. And then 9 times 6, that's 54. No square root there anymore. All right, 28 times 2. That gives me what? 56 square roots of 3 plus 21 times 2, that's 42 square roots of 6 minus 12 times 3 is 36 square roots of 2 minus 54. And notice we have it all simplified, but we can't combine any of those terms. All right, we leave it like that. That is our final answer, 56 square roots of 3 plus 42 square roots of 6 minus 36 square roots of 2 minus 54. Let's take a look at one more example here. Again, we have to distribute, but I see a beautiful thing. I see 8 square roots of 5 minus 6 square roots of 3 times 8 square roots of 5 plus 6 square roots of 3. Notice they are both the same factors, except the sign is different in the middle. You might remember this as like x minus 2 times x plus 2. Those are called conjugates. Right? The same two terms, the same two binomial terms. The only thing difference is the sign in the middle. And the beautiful, beautiful thing about conjugates is that we know that the middle two terms always cancel out. Like this right here. I'll multiply this one up real quick here. This x minus 2 times x plus 2. That was x squared plus 2x. And the inner terms would be minus 2x. And then the negative 2 times the positive 2 would give me negative 4. Right? That plus 2x minus 2x. Right? The O and the I of FOIL, those middle two terms on conjugates, they always cancel out. And this one, for example, would give me x squared minus 4. Right, so let's apply that to multiplying these binomial radicals, as we call them. So I've got to distribute my 8 square roots of 5 with the 8 square roots of 5 and the 6 square roots of 3. And then I got to go ahead and I got to distribute that negative 6 square roots of 3 with the 8 square roots of 5 and the negative 6 square roots of 3 times the positive 6 square roots of 3. Okay, so let's go ahead and do that. We got 8 square roots of 5 times 8 square roots of 5. Well, 8 times 8, that is 64. And square root of 5 times square root of 5, that is 5. Okay. Now, let's multiply 8 square roots of 5 times 6 square roots of 3. So 8 times 6, that's 48. And square root of 5 times square root of 3, that's square root of 15. All right, now go to distribute our negative 6 square roots of 3. So negative 6 square roots of 3 times 8 square roots of 5, that's going to be minus 6 times 8 is 48. And square root of 3 times square root of 5 is square root of 15. And then finally distribute negative 6 square roots of 3 with positive square roots of 6 square roots of 3. Negative 6 times positive 6 is going to give me negative 36. And square root of 3 times square root of 3 is 3. All right, now this is what I'm talking about with the conjugates. When we multiply conjugates, these middle two terms always drop out. And that's the beautiful thing about conjugates. When you see the same two binomial terms multiplied together, only they have different signs in the middle, you know that those middle two terms are going to drop out. So here's a situation where actually I only need to do the F and the L of FOIL. I only need to multiply that 8 square roots of 5 times 8 square roots of 5 and the negative 6 square roots of 3 times the positive 6 square roots of 3. Because I know that the other two terms are going to multiply out. I know that I only have to multiply the first terms and the last terms. Right? That only works for conjugates, though. All right, so don't be doing that with all those other things. Okay, let's finish this off then. Okay, so the middle two terms, they cancel out. I got it. And I just have, now all I have left is 64 times 5. What is that? 60 times 5, that's 320. And then the 36 times 3, what is that? 3 times 30 would give me 90. And I need another 18, so minus 108. Minus 108. So I have 320 minus 108. So 320 minus 100, that's going to give me 220 minus another 8, gives me 212. And there's our final answer. Notice how that really simplified on this example. And that was because we had conjugates. All right, you guys have fun with it now.